Hi everyone, and thank you for tuning into this talk. My name is Roei, and this talk is titled on Exponential Time Hypothesis, Derandomization, and Circuit Lower Bounds. And it's based on a joint work with Lijie Chen, Rothblum, and Eylon Yogev. And our starting point will be the ETH exponential time hypothesis by Impagliazzo, Paturi, and Zane, which says that for some epsilon, 3 sat with a linear number of clauses takes time 2 to the epsilon n to solve. So this is an exponential version of P does not equal NP, because it says that for a specific NP problem, there's a lower bound which is exponential 2 to the epsilon n. And I'm going to note in advance that there's also a strong version that we will not focus on this talk. The strong version essentially says that epsilon can be taken as close to 1 as we want for k sat with a large k. But we're not going to focus on this. We're focusing on the standard ETH, which just asserts a lower bound of 2 to the epsilon n. And a natural extension of ETH is to assert that the lower bound also holds for randomized algorithms. So randomized algorithms can solve 3 sat in time 2 to the epsilon n. And this can be thought of as an exponential version of the statement that NP is hard for BPP. So we get an exponential version of the classical conjecture NP is hard for BPP. And along the same line, we can take an exponential version, for example, of co-NP is different from NP. This is the non-deterministic ETH, which says that co-3 sat is exponentially hard for non-deterministic machines. So the hardness will again be 2 to the epsilon n. And you know, we can do this all day. We can take any classical complexity conjecture, for example, a separation of AM from co-NP or of sharp P from P, and this will be a sort of exponential time hypothesis. So together we call these exponential time hypotheses with an E, and these are the ETHs. And they've been studied in recent years. And just to note, all the hypotheses in this slide might as well be true. We have no evidence against them currently. So the strong version of MA-ETH was refuted several years ago, but this was the strong version. And here, these are the weak versions, just lower bounds 2 to the epsilon, and they could be true. And they've been broadly influential in complexity theory. They've influenced many fields. For example, structural complexity, defining classes based on hardness, or communication complexity, and parameterized complexity, and fine-grained complexity, etc., etc., etc. These are central hypotheses. And in this work, we focus on the connections of ETHs to derandomization and circuit lower bounds, which is a very natural connection to focus on. And in a gist, our main contributions is in showing that even very mild ETHs have far-reaching consequences for derandomization and for circuit lower bounds. So when we assume ETHs, we also assume a lot about what happens in the world of derandomization and circuit lower bounds. And we prove this via a sequence of results that are each of independent interest to long-standing questions. In this talk, I'm going to present 2 main results from our work. And for the first result, I'm also going to sketch some high-level ideas from the proof. In the end of the talk, I'll briefly mention extensions of these results as well as other results from our work. So let's begin with the first result. Our first result asserts that under RETH, randomized exponential time hypothesis, we get a very fast derandomization of BPP. Namely, that BPP can be deterministically simulated in almost polynomial time on average case. And I will elaborate later on what almost polynomial time and on average case precisely mean. Now, this result belongs to the line of works that is typically called hardness to randomness and convert lower bounds to the randomization algorithms. And specifically in our case, we start with a uniform lower bound for uniform probabilistic algorithms. So we're concerned with the special case of uniform hardness to randomness, which is indeed a well-studied special case. And the results in this line of work look like our result. Assuming lower bounds for BP time, they get average case derandomization of BPP. And what do we expect to get with this type of result? Well, intuitively, the stronger the lower bound that we start from, the faster the derandomization that we expect to get. And one can show that the optimal trade-off should look about like this. we start from a function in exponential time that is hard for BP time TLB. This is T of the lower bound. And we deduce that BPP can be simulated deterministically on average in time T Derand, which is D of the derandomization. And we expect the graph to look like this. The stronger the lower bound, the faster the derandomization. Now, unfortunately, prior to the current work, what was known looked as follows. Well, first of all, instead of starting with a hard function in exponential time, we start with a hard function in p-space, namely TQBF, or totally quantified Boolean formula, which is p-space complete. And secondly, indeed, while starting off with the weak lower bounds, when we strengthen them, we do get faster derandomization, but this trend line stops at some point. Even if we strengthen the lower bound further, the derandomization does not become faster. And the part of the graph in which we expected to get faster derandomization but didn't is typically referred to as the high-end setting. High-end meaning stronger lower bounds, and we expect to get high-end, faster derandomization, but couldn't get it. And there have been many ways to bypass this challenge previously. For example, to move to a non-deterministic setting and prove things there, or to start with an inherently stronger hypothesis, for example, hypothesis in fine-grained complexity or the strong exponential time hypothesis, or simply to prove that this trade-off that we want to get is in some sense necessary. And loosely speaking, what we get in the current work is simply we attack the problem directly and manage to significantly extend the trend line and show that stronger lower bounds do indeed imply faster derandomization for a large setting of parameters. And let's be a bit more technical about this. So I want to note that RETH or ETHs in general don't imply truly exponential hardness in terms of the input length. Because the three-set formula on, say, V variables takes V log V bits to represent. So when we assume hardness 2 to the epsilon V, we actually assume hardness that is slightly below exponential in terms of the input length. We assume hardness 2 to the epsilon n over log n. So what was previously known for such hardness? 2 to the n over, and let's generalize, 2 to the n over polylog n. And not going into detail, the last line, the previous state of the art by Trevisan and Vadhan, asserted that given such lower bounds for TQBF, we get the randomization of BPP in quasi-polynomial time, 2 to the polylog n. And now it's time to formally state our result. So we assume indeed that TQBF cannot be solved in probabilistic time 2 to the n over polylog n. And I want to know that this assumption is weaker than RETH. If we assume RETH, we do get this assumption. And this is because RETH asserts hardness for 3-sat, and 3-sat can be reduced to 2QBF in linear time. So under this assumption, and in particular under RETH, we conclude the following derandomization of BPP. For every L in BPP, there exists a deterministic algorithm, A sub L, that runs in time n to the poly log log n. So note the double log in the exponent. This is n to the poly log log n, and this is the correct running time that you expect to get from this type of hardness. And the deterministic algorithm solves L in the following sense. For every polytime distribution over the inputs, the probability that the distribution hits a bad input for A sub L, an input on which A sub L fails to decide L, is negligible. And it's useful to think of this adversarially. Any polynomial time algorithm that tries to find an input on which A sub L fails succeeds with at most a negligible probability. So this is the meaning of average case, on average, that I noted before. And before moving on to the proof, let me just mention the remaining gaps between our result and the ideal result that we'd like to get. Well, first, we handle hardness of the form 2 to the n over polylog n, but we don't handle this purely exponential hardness 2 to the epsilon n in terms of the input length. which we ideally expect to give a fully polynomial time simulation of BPP. And also, and maybe more interestingly, the function that we assume hardness for is TQBF, is in p-space, whereas ideally we'd like to start from hardness for a function that's computable in exponential time. Let's go over some high-level ideas from the proof of this result. Our goal will be to construct a pseudo-random generator, a PRG, which is a machine G that takes as input a short random string with ln bits and outputs a much longer string with n bits, whose purpose is to full efficient distinguishers. So a distinguisher is a procedure that looks at an n-bit string and tries really hard to distinguish the output of a PRG from a truly uniform random string. And we will be concerned with a particular type of PRGs that are called reconstructive PRGs. So with this type of PRG, we base the PRG on a hard function f, denoted gf. And the main argument is a reconstruction argument. It says that if there exists an efficient distinguisher for gf, then we can transform it to an efficient procedure that computes f. And we model this reconstruction procedure as an oracle machine. So we have an oracle of reconstruction that gets access to any distinguisher and computes the hard function f. And why does a reconstructive PRG work? What's the point of this reconstruction argument? Well, we assume that f is hard. Therefore, there does not exist any efficient procedure for f, meaning that there also does not exist any distinguisher for the PRG. And note that the main bottleneck in this argument is the reconstruction complexity, because the more efficient the reconstruction that we can prove, the tighter the hardness to randomness results that we get. Now, in our particular case, we start with a uniform lower bound, the lower bound for uniform algorithms. And therefore, we must also prove a uniform reconstruction argument. Now, you can show that this is impossible without any assumptions on f. It's impossible for an arbitrary f. And Impagliazzo and Wigderson about 20 years ago showed that it is nevertheless possible when f has some structure. And specifically, it's possible for some functions in p-space. However, their argument involves large overheads. And our starting point is an idea of Trevisan and Vadhan from the early 2000s, which is to construct a tailor-made hard function, f, that is reconstructible, meaning that we can construct an efficient reconstruction algorithm for f. And specifically, their function was an artificial p-space complete function for which they showed an efficient reconstruction argument. And this idea underlies the previous state-of-the-art result. And let's see logically what's going on here. So we start from hardness for a natural function, for example, TQBF. And by a reduction to this artificial function, we get hardness for this artificial function. And since this artificial function is efficiently reconstructible, we get that the reconstructive PRG works with hopefully as low as overhead as we can. And our main technical contribution is to construct a super efficiently reconstructible function f, meaning a function f that both has a super efficient reduction from TQBF and that has a super efficient reconstruction algorithm for the PRG. We then instantiate the PRG reconstructive argument in a modified way, but that ensures that it has a minimal overhead, and we get a tight, uniform hardness to randomness result for the high-end setting. And to mention just very quickly what's going on, so our function f will be a different artificial p-space complete function. And the original function of Trevisan and Vadhan was based on the IP equals p-space protocol. And our function is also based on this protocol, but in a condensed form, with only polylog n rounds and with some modifications. And since this function might be useful for others or for other works, let me just mention some key properties that it has. Well, it has a reduction from TQBF in near linear time, in time O tilde of n. It has specific and special kinds of downward self-reducibility and random self-reducibility that are useful for our particular proof, and it has an additional somewhat odd property that can support an extension of these results to an almost always version. Okay, so now we are ready to move on to our second main result in the paper. And to do so, we need to make a context switch in our heads. So far, we discussed a uniform setting, lower bounds for uniform algorithms and corresponding average case derandomization. Now we need to switch context to a non-uniform setting, meaning circuit lower bounds and corresponding worst case derandomization of BPP. And in this setting, we already have a smooth implication. The stronger the lower bound, the faster the derandomization that we get. This was proved in a long line of work starting with Nissan Wigderson in '94 and culminating with Umann's work in about 17 years ago. And the main question of interest right now is whether or not the same lower bounds are also necessary for worst case derandomization. Is it an if and only if? To visualize things, the first implication is that circuit lower bounds smoothly imply derandomization, which we mentioned. And the second implication that we also know is that derandomization in turn does imply circuit lower bounds, albeit weaker ones. So as one particular example, if E is hard for exponential size circuits, then promise BPP equals promise P. And if promise BPP equals promise P, then we get on the right-hand side the weaker lower bounds of the form NP is hard for circuits of fixed polynomial size. And now I can introduce what I'm going to call the equivalence conjecture. And this conjecture asserts that the randomization of BPP is completely equivalent to specific corresponding circuit lower bounds against E. So essentially we get an if and only if. For example, E is hard for exponential size circuits if and only if promise BPP equals promise P. And this conjecture not only says that the two problems are essentially the same problem in disguise, which is staggering, but it also implies a canonical black box way to do the randomization. It says that if the randomization is at all possible, then it is possible using PRGs in a black box way. And our result is the following. Assuming the non-deterministic exponential time hypothesis, the equivalence conjecture is true. Derandomization and circuit lower bounds are indeed completely equivalent. And in fact, we prove this under a significant weakening of the non-deterministic exponential time hypothesis, and we also show a partial reverse implication. So conceptually, this provides appealing evidence that the equivalence conjecture is true, assuming this weak form of the non-deterministic exponential time hypothesis. And it also shows a sufficient and essentially necessary path to prove this. Now, while the formal theorem involves some technicalities that I don't want to go into, let me just mention that this weak version of NETH involves lower bounds for n-time uniform circuits, which is a class that this is a seemingly weak subclass of NP cap co-NP. Finally, let's now do a quick recap and mention some additional results from the paper. What we've seen so far is that RETH implies a very fast randomization of BPP, and that NETH implies that the randomization and circuit lower bounds are completely equivalent. And one can reasonably ask what happens if we go further up the ETH's hierarchy to a stronger exponential time hypothesis. So there we have an easy answer. If we assume MAETH, the exponential time hypothesis for Merlin-Arthur, then we simply get that the strong circuit lower bounds are true, and therefore also we get a worst case randomization of BPP. So in a gist, assuming MAETH already gives us the answers to the main questions in derandomization and circuit lower bounds. And this is not difficult to prove using strategies from classical Karp-Lipton theorems. Therefore, our focus is on weaker hypothesis below MAETH. And lastly, I'm going to mention several other results. So first of all, theorem 1, which refers to RETH, also extends to an almost always version, which makes significant progress on a technical challenge in this type of results so far. Theorem 2, with respect to NETH and the equivalence conjecture, scales to many parameter settings, albeit non-trivially. And two other results are the following. First, we show that randomized circuit analysis algorithms imply lower bounds, circuit lower bounds. Specifically, if circuit SAT can be solved in probabilistic time 2 to the n over polylog n, then we get new lower bounds for superlinear sized circuits. And in addition, we prove a new Karp-Lipton style result. If BPE, probabilistic exponential time, has circuits of superlinear size, then we get a very fast derandomization of BPP. BPP can be deterministically simulated in almost polynomial time on average. That's it, everyone. More details appear in the paper. Thank you very much for listening.